Hello friends, today we will look at the idea of time division multiplexing. We've already seen that a band limited signal can be perfectly recovered from its samples if the samples are taken at a rate greater than twice the maximum frequency of the signal. So as per sampling theorem, we need not transmit the continuous time signal for all the time. Rather, we can just transmit its samples which are separated in time called the sampling interval. Now, for that time, the time gap between two successive samples, the channel remains free, unutilized, and that time can be utilized for transmitting the samples of other signals. And this idea is called time division multiplexing. Let us try to understand it. So suppose we are transmitting the samples of a signal, and one practical way of sampling is flat top sampling, or also called pulse amplitude modulation. So suppose we transmit the first sample of our message signal, let me call it 1, at 0 instant. The second sample must occur after the sampling interval has elapsed, and let's say that this is the second sample of the message signal at TS, and the third sample, suppose, is like this, which occurs at 2TS, and they all belong to the same message. This is the second sample of the message, and there is a third sample. So I'm writing 1, 2, 3, and I will represent it in black color. But you can see that this time interval from 0 to TS, for this time the channel is not transmitting anything, and therefore it is unutilized. So this time slot can be used to embed samples from other messages. So there is, say, another continuous time signal whose sample I am representing by this blue color now. So I am transmitting the first sample of this signal here, the second sample of this second message signal here. So this is the sample, the third sample of the second message here, and so on. We can go on, we can have yet another signal whose sample I can, because some time is still available, can be fit here. The first sample of the third message, the second sample of the third message, and so on and so forth. Right? So this idea is called time division multiplexing, and because here the sampling has been done in the form of pulse amplitude modulation, this whole scheme is called pulse amplitude modulation time division multiplexing, or a PAM-TDM scheme. The whole idea is shown here. In general, we can multiplex samples from n different continuous time message signals. So there are n message signals designated as M1T, M2T, M3T up to MNT. They are first band limited through low pass filters so that the sampling theorem can be followed and no aliasing occurs, and that is the reason why these low pass filters are called anti-aliasing filters. There is a commutator R which keeps on taking samples from these messages successively. First it takes the first sample from M1, then the first sample from M2, then first from M3, and so on. And after TS interval, it takes the second sample from M1T, and then from M2T, and so on. It continues, and you can see here that M11 denotes the first sample of first message signal, M21 is the first sample of second message signal, M2T, M31 denotes the first sample of M3T, and so on. And this way the samples are obtained and they are transmitted through the channel. At the receiving end, the receiving arm of the commutator is synchronized with the arm at the transmitter side, and therefore these samples are separated as shown here. We get first sample of first message, second sample of second message here, first sample of second message, second sample of second message, and so on here, and so on. and then these samples are smoothened through low pass filter to get the best estimates of the transmitted signal M1T, M2T, and so on. We have denoted them here as M1 tilde T, M2 tilde T, and so on. So these low pass filters basically are used for reconstruction purposes. So they are called reconstruction filters. This way, time division multiplexing gives a way for efficient utilization of channel for all time. Of course, there is still some gap provided between two successive samples, sample from two different message signals, and that we denote as the guard time tau g. The pulse width is capital T. We'll see in a subsequent lecture the importance of the guard time, the pulse width T, and their relation with the sampling interval Ts. For now, it is sufficient to know that this advantage of time division multiplexing doesn't come for free. There is a cost involved, and that cost is in terms of, number one, the transmission bandwidth, which increases because there are n signals now. If all the signals are band limited to say W hertz, then the transmission bandwidth for n such signals would be n times W. So at least NW is the transmission bandwidth. If I denote that by FB, transmission bandwidth, so that must be greater than or equal to n times W. And the second thing is more important to understand is that when two pulses close by are transmitted through the channel, they give rise to an effect what is known as crosstalk. Let us try to understand the same. Note that the pulse we are transmitting is a time limited pulse of some fixed width t, and we know from our knowledge of Fourier transform that a time limited signal cannot be band limited. So this is time limited, so it has to be band unlimited. That is, it occupies infinite band. So band unlimited. Interestingly, the channel that we use for transmission, it is a band limited channel. Channel is always a band limited channel. It can only allow certain frequencies to pass through it and will reject or attenuate others. And when a band unlimited signal is passed through a band limited channel, that band limitedness of the channel curtails some frequency part of this pulse, and now at the output the pulse becomes band limited pulse. Okay, so now we have a band limited pulse, and because the pulse has now become band limited, so it becomes time unlimited. That is, it disperses in time unlimited pulse. That means when you have transmitted this pulse, what we receive at the output at the receiving end is not this rectangular pulse, but it has already spreaded in time because of the band limiting of the channel. And because this pulse is now occupying higher time than capital T, we are not just transmitting one pulse, there is another pulse we are also transmitting. That pulse also disperses because of the same phenomenon, and what happens is that successive pulses overlap. The same happened with the previous pulse also, and indeed that overlap may not just be to the successive pulse, it may last for even more number of successive pulses, and this overlap leads to a distortion and what we call crosstalk. So crosstalk is one of the major impairments in communication when we want to utilize the channel for all time or as much as possible. So that comes at a cost of a distortion because of overlapping of pulses of two different message signals, and that phenomenon is known as crosstalk. We will further analyze this idea of crosstalk and the effect of guard time and the pulse duration on it in the next lecture. Thank you.